in chemical engineering from Columbia University, New York. And yes, I'm checking here. We are recording, okay. And his research was very much related to his presentation today. I think that the title of his his PhD thesis is the same
Yeah,
of
that's true.
his presentation today. So he worked with building domain-informed language models for process engineering, systems engineering. Um, During his PhD, Vipul published more than 10 journal articles. He also presented at several American and international conferences. He won the third place award at the Computing and System Technology division at AICHE annual meeting last year, and also filed a USA patent application based on his doctoral work. He, prior to his doctoral university studies, Vipul earned his bachelor's and master's degree in chemical engineering from the Indian Institute of Technology at Madras. And he also spent 2 years as a data scientist working with problems ranging from anomaly detection, evolution optimization, and sports analytics. Um, he is now working as senior manager biomarker data science at Bristol Myers Squibb. And so we are very glad to have you here, Vipul, today. Thank you very much. Uh, um, our presentations typically you can present your lecture, and afterwards we open for questions
Okay.
and answers. Okay, so thank you very much.
Okay, so I'll start. So thanks so much, Professor Mauricio, for the invitation and for the very nice introduction. So I'll try to do justice to the introduction. You have said really great things about me, and I'm also looking forward to hearing a lot of feedback and a lot of comments on this work because, like I mentioned, I recently finished my PhD, and this is a new area. So it will be very nice to hear everyone's thoughts, questions, feedback on this work. So with that, without further ado, let's get started. So like Professor Maurício mentioned, the title of my talk is Domain-Informed Language Models for PSE. And the focus here is to combine domain knowledge with language models so that they could be used efficiently in PSE. And I had a slide for about myself, but let me quickly cover this because Prof. Mauricio, gave a nice introduction about myself. So currently I'm working as a senior manager of biomarker data science at Bristol Myers Squibb, which is a pharmaceutical company that makes advanced medicines for patients with rare diseases. Specifically for me, I work on causal machine learning, where the whole idea is to find out, personalized treatment regimens for patients and find out what's an optimal patient population for a given medicine. And at a high level, I work with clinical trials data and try to find out insights from those data sets. My journey with chemical engineering started way back in 2012, where I started my undergrad and master's degrees in chemical engineering from Indian Institute of Technology Madras or IIT Madras. And over the years, as I was working towards my degree, got more and more interested in process systems engineering because I was always fascinated with the data-driven side of chemical engineering. Post graduation, I was not sure whether I should do a PhD or not. I was, of course, interested in research, but I was not sure about it. So I spent 2 years in the industry working on a variety of problems, not necessarily in chemical engineering, but worked on anomaly detection, evolutionary optimization, and sports analytics. So that was a pretty cool project that we did with ESPN. A wide range of experience on data science, and I was ready to start my PhD at Columbia in 2019. 2019 to November 2023, I focused on the AI side of chemical engineering, and more specifically, as I mentioned, hybrid AI, where you combine domain knowledge with data-driven methods and techniques. So yeah, that's a pretty snapshot of my professional journey over the last decade. And with that, let's get into the technicalities of the work. So as you may all know, in PSE, the main idea is, you need to find out what's the optimal process design, operation, control, and optimization. And typically, to solve these problems, a wide variety of tools and techniques are used, such as data analytics, modeling, AI, and so on. The process here, as we know, is referring to a chemical or a biochemical process that often involves converting a set of raw materials to desired products. And you often have a flow sheet like the one shown here on the right. At, at the core of PSE or process system engineering is a systems thinking principle. That is, you model a process as systems and subsystems, and then you perform mathematical modeling, and there is an emphasis on interconnectedness between these systems and subsystems. And of course, the application areas of PSE are wide, ranging from chemical, biochemical, food, petrochemical, and all the way up to pharmaceutical and energy engineering. Our focus has always been the AI side of process systems engineering. And AI, it might seem that AI is new in PSC, but that's really not the case. The very first example of AI was in the 1980s, where you had expert systems where you would encode domain knowledge and try to use mathematical programming or computer-based systems to solve problems logically. Then came in the 1990s supervised machine learning, unsupervised machine learning, and more recently reinforcement learning. But very recently, a couple of years ago, there has been a new emerging class of models called the language models, which are typically used for a variety of tasks like machine translation, text modeling, sequence modeling, linguistics, and so on. So the main use case of language models is whenever you have natural language text like English, French, whatever, you would use language models. And the main core of language models is sequence to sequence modeling. So naturally, natural language models, since because of their strong computational capabilities, they also offer a very powerful modeling framework for certain PSE applications. But before they could be used in PSE, there are certain issues that need to be addressed or that need to be fixed before these models could be deployed for PSE. The first issue is that language models, by definition, are pretty complex. They have millions or billions of training parameters, and PSE domain does not really have big data in the traditional sense that can train such complex models efficiently. So you would need really large training data sets if you were to use the standard language models. And the third thing is that unlike computer vision or machine translation, PSE domain is characterized by first principles models, first principles equations. So there is a really rich domain knowledge that is there in PSE, and that should not just be discarded. We should not do purely data-driven PSE, data-driven language modeling in PSE, but we should really marry data-driven modeling with domain knowledge in PSE to solve these problems efficiently. So that's the whole premise of my work, of my thesis over the last 4.5 years. That is, how can you combine data-driven language models with domain knowledge in order to build domain-informed language models for process systems engineering applications. And this would help you solve problems at multi-scale in PSE. And the preview of what is coming next is adaptive problem formulation, developing custom model architectures, coming up with new representations, and enforcing domain constraints. So with that introduction, this is the outline of my talk for today. I'm going to cover a variety of things. At the molecular level, where I talk about reaction prediction, retrosynthesis, and property prediction. In part two of my talk, I'm going to talk about chemical flowsheet modeling and a representation that facilitates the use of hybrid AI methods. And the third part is going to be extracting information from pharmaceutical documents. So let's start with the first part of my talk at the molecular level. So the reaction prediction problem is as follows. So you are given a set of reactants, let's say 1, 2, and up to n reactants, and you are interested in predicting the product of this reaction. So this is known as the forward reaction prediction problem. And this involves, modeling the complex interactions between these molecules, different reactants, to find out the product. And you know that a chemical reaction might have different number of reactants. So you need to be able to take care of that as well. And the application of such a system that can go from a set of reactants to the major product of the reaction is high throughput experimentation, performing dry lab experiments, and even discovering novel chemical reactions. A related problem is the inverse problem, that is going from the product to the set of reactants. So you would want to know how can you synthesize a given target molecule. by identifying the reactants. So this problem is known as the retrosynthesis problem. And the application, of course, are in discovering alternate synthesis routes, for performing synthetic route optimization, and so on. So we formulate the reaction prediction problem in both the directions as a machine translation problem. That is, you would want to translate the set of reactants to the product if you are interested in the forward reaction prediction, or you would translate the product to the reactants to if you're interested in the retrosynthesis problem. So here, translation is similar to what you would do while translating English to French or French to English. But since we are using a machine translation framework, we need a text-based representation of molecules, because machine translation framework would work if you have natural language like text. So we look at molecules as words, and each molecule is represented using their SMILES strings. So I'm not sure if everybody is aware, but let me give you a brief overview of SMILES representation. So SMILES representation stands for Simplified Molecular Input Line Entry Scheme, which is a linear text-based representation of molecules. For example, if you have something like this, which is for propene, the SMILES representation would be C, C, this equals to or double bond sign, and then C. So it's a very linear way of representing molecules. If you have a more complex molecule like this, you would have this as a SMILES string. So there's a deterministic way of extracting canonical SMILES strings from molecules, and we use them as words in this framework. So now that you have a collection of words, each word corresponding to each molecule, you can say that this is one sentence and this is one sentence. And now you can use a machine translation model like a transformer model. So I guess people might be aware of transformer models because of ChatGPT, because ChatGPT under the hood, it has a transformer model, which is much more complex and advanced. So we're using the same model here, but for chemistry applications. So you can use this model, the transformer model, to learn some parameters and translate from this sentence to this sentence for the forward prediction, or from this sentence to this sentence for the inverse prediction. Now, this framework was not proposed by us. This was done, I guess, in 2019. But in this framework, there are a lot of limitations that need to be addressed before we could, use this in real life. The challenges are as follows. So if you look at this reaction, which is, by the way, for the cumene process, you have benzene reacting with propene in the presence of oxygen to give rise to phenol as a main product. And these are the SMILES representations. So you can see that in the SMILES representation, it's a purely text-based representation, and there is no explicit structural information. A lot of structural information is lost, and that is by definition because SMILES strings are overly simplified of a molecule. Second, since we're using a machine translation framework for translating the molecules to the product, there is no constraint as to whether your predictions are going to be syntactically valid or not. Just like in English language, while translation, you might make some grammatical mistakes. Similarly, you might make some grammatical mistakes while using such a framework for predicting reaction outcomes. And finally, since we are talking about a very complex model here, there is obviously a risk of overfitting, because when you have millions of parameters and not enough data set, you would have overfitting risk. So how do we address these issues? And on top of this, when you look at the retrosynthesis problem, your objective is to go from single molecule to multiple reactants, to predicting multiple reactants. So this becomes a combinatorially much more difficult problem, going from one molecule to multiple molecules, because there's so many possibilities. And as you will see in the coming slides, the retrosynthesis data is much smaller. It is 1/10 of what we have for the forward reaction prediction problem. So even a normal training would be challenging. So how do we address all of these issues? So we need to adapt the problem formulation from a chemistry standpoint so that these problems could be either completely eliminated or should be mitigated to a large extent. So before I show you and talk about the adaptations, we also need to look at something called SMILES grammar. So remember that I mentioned SMILES representations are considered as words. So just like you have a grammar for English language or for any natural language, there is also grammar for SMILES representation of molecules. And this SMILES grammar is similar to, like I mentioned, the context-free grammars for English language, which was proposed and formalized by Noam Chomsky in the year 1956. So it goes a long way back, and linguists have developed a very formal way of representing grammar. And the Smiles grammar equivalent of that looks like this. So basically, what this grammar is that it is a finite collection of recursive rules where you have, if designated start symbol smiles, which indicates the start of a grammar, which is, it's like a placeholder. And then you have a set of non-terminal symbols which capture the chemistry. It's saying that, something could be a chain, something could be a branch atom, something could be a ring bond, and stuff like that. So this really is encoding your chemistry information indirectly. And then you have a set of terminal symbols, or basically the symbols that you would use in a smiles representation. So the equals to sign, the C character, all of these are terminal symbols. And the rules, the production rules, or the recursive rules are these. So A goes to B, so that defines one production rule. So in this way, the grammar is formalized using a set of these four symbols. Now, one of the applications of grammar, as you may recall, that if you have in English, if you have a sentence, if you understand the grammatical structure of that sentence, you have much more information about that sentence rather than just having a collection of few words. Similarly, we use a Smiles grammar for assigning structure to a Smiles string so that we have a lot more information about a Smiles string rather than just using the Smiles characters or tokens only. What I mean by that is, and here also comes a first adaptation, that is coming up with a new representation that is more chemistry informed. Again, let's take a look at the same example, propene, with a Smiles representation of C double bond C. When we use the Smiles grammar, we get the following as the grammatical tree structure. So this tree structure is basically encoding all the grammar rules that you need to apply to arrive at the Smiles tokens, the Smiles characters C double bond C double bond C as the leaf nodes. So basically, this is providing you a structure, giving you some chemistry insights into how these atoms and bonds are connected with each other explicitly. And now this is a tree structure, and we need a word-like representation. We extract the Smiles grammar representation by saying that I'm going to start at the top, and I'm going to extract all the grammar rules which were applied to the previous token in a depth-first manner. That is, I start at the top, go all the way down to the bottom. So I extract 1, 3, 2, 4, 6, 15, 1, 3, 2, 4, 6, 15, 17 from the left branch. Then I go back up to the next branch, and then so on. So in this way, I have a flattened tree representation, which consists of not only my Smile string tokens, but also the intermediate information. And this, you can clearly see that this is much more chemistry rich. And our objective is to use these representations and not the Smiles representations in the machine translation framework. Because you can see that the chemistry component in this is much more than just these four characters here, because they are based on a formal grammar. And the second thing is that since now we are training a machine translation model using the grammatical structure and not the sentences, we are forcing the model to learn the underlying grammar first. So this is going to make sure that, or maybe the hope is that this is going to make sure the model will not make grammatically incorrect predictions. And the third thing is that we have also shown that this is better from an information theoretic standpoint. So I won't go into the details of this. So I refer you to these papers if you want to look at the information theoretic superiority of the grammar-based representations. But I'll talk about the results and the better results that we get with grammar representations. So this works great, like I mentioned, and you'll see in the results. But then, as I mentioned, the retrosynthesis problem is much more difficult. So for that, we need two more adaptations. So the adaptation number 2 for the retrosynthesis problem is that we formulate the retrosynthesis prediction problem as a tree to sequence problem instead of a sequence to sequence problem. What I mean by that is, instead of giving a flattened representation by extracting all the grammar rules like we extracted on the previous slide, I'm going to give the entire tree as input to the model, and I will predict the reactant smile strings here. So since I'm utilizing the entire grammar tree hierarchy, I not only know the intermediate chemistry information, but I also know the hierarchical structure of the tree, which will provide me some more contextual information while making the predictions. And finally, we are at the target. We have the smile string of the reactants. because we are not interested in the grammatical structure of the reactants, but we just want what molecules that I need to synthesize this target molecule. So this is a tree to sequence formulation. You're going from a grammar tree to the sequence of smile strings required to synthesize this molecule. And the third adaptation and the final adaptation is that we introduced something called tree convolution blocks so that we could handle trees as transformer inputs. So what I mean by that is if you have a grammar tree like this, for each node, I will perform convolution operations. So I will look at the parent node and the children node, and I'll try to combine them together using some form of transformation functions. And the idea behind this is inspired by group contribution theory, where the idea is that the properties of a molecule is determined by the functional groups underlying that molecule. So in this way, we are indirectly or automatically extracting functional groups from the grammar tree and then using that as input to the transformer. And this led to a change in the model architecture. So this is the standard transformer architecture, which was proposed by the computer scientist in 2019. But then we adapted the transformer architecture by introducing these tree convolution blocks, which capture some chemistry rules and some chemistry information indirectly. So now that we have seen the adaptation, let's take a look at the data set that we use to train the model and the results. So this is a standard data set that people in this work have been using for quite some time. For the forward reaction, we have the USPTO forward reaction data set, which has about 500,000 chemical reactions. So we perform the training, validation, and test set splits. And as I mentioned, you have 1/10 the size of the forward reaction data set. So you have about less than 50,000 reactions, and then you need to train your model, validate, and test your model on these many reactions. And to assess the performance of the model, we define a bunch of metrics. The first metric is accuracy, which is the perfect match between the prediction and the ground truth. For example, if you for the forward prediction, given a set of reactants, let's say this is the true product that is going to be formed, and this is the predicted product. So in this case, since the prediction does not match the ground truth, the accuracy would be written as 0. The second metric that we define is syntactic validity. That is, what fraction of predictions were at least grammatically correct. I don't care whether they exactly match the product or not. As long as they are grammatically valid, I'm okay. So the smile strings in both the cases were grammatically valid. So this becomes 1. Then we also define something called similarity score, which captures the similarity of the smile strings between the prediction and the ground truth. And that number comes to 0.74. And again, for retrosynthesis, we had to define one additional metric because here, again, you are going from one molecule to a set of reactants. So the accuracy in this case would mean that both the molecules have to be predicted exactly right. Only in that case, you would have 0. But then that's a very strict measure. So we define something called maximal fragment accuracy or max frag accuracy, which is basically the accuracy of predicting the longest reactant molecule. So I don't care about the entire reaction set. If I'm predicting the longest molecule, which is this in this case correctly, I mark this as 1. So bunch of metrics for assessing and trying to get a sense of how good the model is performing. So let's take a look at the results. And all the results which I'm going to show on the next slide are on the test set. That is, these reactions were not seen by the models during any stage of the training. They were completely held out data set. So here's the result for the forward reaction prediction. So the top 1 accuracy is 80.1%. That means in 80% of all the predictions on the test set, my model exactly predicted what's going to be the product of the reaction given the reactants. The syntactic validity is 99%, meaning that only 1% were grammatically incorrect, and the average similarity score across the smile strings of the ground truth and the predicted were 95.8%. We further bin this into 3 bins with more than 95% similarity, more than 85%, more than 75%, and we see that about 84% of all the predictions had at least 95% similarity. So incorrect predictions are still very close to the ground truth, and that points towards the fact that the model is learning something. Then we also did some interesting exercise. So we compared our data set, our model performance on a separate data set, and compared our model performance against human organic chemists. It would be nice to see how well the model is performing against real chemists. So this dataset had 80 reactions across 8 different categories of reactions. So here's the results. On the horizontal axis, you see different reaction categories. So basically, as you go towards the right, the reactions become more and more difficult, more and more rare, so they become difficult to predict. And on the vertical axis, you have the accuracy of predicting them. The blue curve shows the human accuracy. So there were about 10 different humans, different professors, grad students, and all of them. And so there's a variety of human organic chemists that were given these reactions. And this is their average accuracy, the blue curve. And the red curve is basically the model accuracy. So we see that the model outperforms the human organic chemist consistently across all the chemical reactions, except for the difficult ones where they both perform equally well or equally bad. And finally, we also compared our model with other works in this area because, like I mentioned, we were not the first ones to use machine translation, but we were the first ones to use Smiles grammar. So we see that if we use the Smiles grammar, we significantly reduce the number of parameters that our model has, and without giving away accuracy too much, or in certain cases, we even outperformed a model with 30 million parameters. So this was about forward reaction prediction. Let's look at the results for retrosynthesis. For retrosynthesis, again, the same set of metrics. Accuracy was 51%. So you can notice that we have gone from 80% to 51% because retrosynthesis is much more difficult problem. And here you're comparing accuracy of predicting the entire set of reactants accurately. And you don't just have one molecule, but you have a set of reactants to predict. So that's why the accuracy drops. But then if you look at the top 10 most likely predictions and compute the accuracy, it goes up to 79%. The max frag accuracy, the accuracy of predicting the longest reactant correctly, is 60% and goes up to 84%. And so again, we can see that we have a fairly high accuracy and fairly high max frag accuracy. And to further understand the model well, we define something called max frag BASR or bioactivity similarity rate. So we see that if two molecules have a Tanimoto coefficient of more than 0.85 computed like this, then we say that the two molecules are bioactively similar. So we see that even for max frag BSR, we reach 95%, meaning that even though our accuracy might be 51% or 60% for max frag, the bioactivity similarity rate is still very high. That means that the model might have gotten one functional group wrong or a very small mistake, and because of that, they might still have the same bioactivity, but then they were penalized because they did not match the ground truth exactly. And then, of course, we also compared our work with other works in this area. And this is our work's performance. So you have the top K accuracy, and then here you have the invalid predictions, the grammatically invalid predictions. So we see that we achieve nearly state-of-the-art performance, meaning that we achieve nearly the best performance across all the works in this area if you look at the invalid rate and the accuracy of this. So in summary, we have seen that adding adaptations to forward reaction prediction models and retrosynthesis prediction models not only simplify your training task, not only simplify your model architecture, but it also improves the performance of your models as well. And now shifting gears a bit, and let's look at a simpler problem, relatively simple problem, that is molecular property prediction, which involves going from a molecule to predicting some property like, let's say, boiling point, critical temperature, drug activity, and so on. So mathematically, this problem involves going from a quantitative molecular representation, let's say of a vector of size m, and learning a function transformation that can give you the property accurately. A standard way of doing this would have been taking all the molecular descriptors, atomic weight, surface charge, total surface area, and so on, and building a predictor vector and then trying to build a model. Our approach was again connected to Smiles grammar because we saw that Smiles grammar works really well for reaction prediction. So we hypothesized that this is also going to work well for property prediction. So we use Smiles grammar and we use a representation learning framework to learn a vector-based representation and then train a machine learning model to predict properties. And the inspiration for this came from Word2Vec. So again, I'm not sure whether everybody is aware of word2vec, but word2vec is an approach in natural language where you can learn vector representation of words, and you can also preserve context while learning those vectors. So they are not random vectors, they really preserve context. And when I say preserve context, I mean the following. So it's a very popular example. So if you take the vector of king and you subtract, perform an arithmetic subtraction for the vector of man and add the vector of woman, you would get a vector of queen. So basically, you can see that this is preserving context in the sense that you preserve the royalty, but you change the gender by performing this subtraction and addition, and you get a vector which is very similar to queen. So this is what I mean by contextual preservation. And we wondered how would a word-to-word framework for molecules would look like. So we took the same idea, we trained something called grammar-to-word by again treating Smiles's grammar tokens as words and molecules as sentences. And then the details, the technical details of that, you would find in this paper that we published. But I'm going to present the results in the interest of time. So basically, grammar-to-vec is what word-to-vec is for natural text. This is for molecules. So regression statistics. So we had two properties of interest, boiling point and critical temperature. And we selected these properties because we were talking to a collaborator and they said that, if you can get these two right, the other physical properties should not be too difficult to get them right. And primarily, you also see that boiling point has about 3,400 data points, whereas this one has much, much fewer data points, only 800 data points to train. So, and here are the results. So you see that grammar2vec performs pretty well with an R squared on training side of 0.93 and R squared on test side of 0.91. And for critical temperature, again, you see a pretty good R squared and pretty good fit between the actual and the predicted values. And just to be sure, we also compared Smiles to Vec, ignoring all the grammatical information, only using the Smiles representation. And we see that the performance is much worse compared to grammar to Vec, both for the boiling point and the critical temperature data set. So again, this points towards the fact that adding more chemistry information increases the performance of the model and also simplifies them to a large extent. Here's some results on the error distribution. So you see that for the grammar2vec results, we have all the molecules on the x-axis, the index, and we sorted the plots based on the relative absolute error. So we see that 95% of all the predictions were within 10% error, 82% were within 5% error, and so on. And something interesting that we saw was the fact that if we only take hydrocarbons, so we remove everything else, we only take hydrocarbons and retrain grammar2vec, we see a much, much better improvement in model performance. So 98% or 99% of all the predictions were within 5%, and this number was 82% here. So having a bigger data set, having a slightly more uniform data set helped grammar2vec to learn better contextual representations as compared to taking the entire data set. Now again, we did some sort of bunching like how does the performance change with respect to molecular complexity, what are the feature importance, and then also correlating the insights that you get from the machine learning model with physical understanding of chemistry and so on. So you should be able to find all of that details in this paper, but in the interest of time, I'm going to move on to the next slide. But yeah, so until this point, we have seen how incorporating more information, adapting the model architecture helps in predicting the property of interest with more accuracy. And we have seen that for reaction prediction, retrosynthesis prediction, and property prediction. Now let's go to one level higher and look at chemical flow sheet representation and generation. So again, the whole idea behind process flow sheet synthesis and design is to find out a way of converting the raw materials to products. And this involves two problems, synthesis and design. So synthesis involves identifying the reaction scheme, the unit operations, their sequence, and the design problem involves finding out the design parameters, the operational parameters, and so on. And they're often solved hand in hand, parallelly. And the thing is, as you have more complex flow sheets, more complex unit operations, things become computationally inefficient and they become very complex. The question is, can we use AI or hybrid AI to address these issues and perform flow sheet synthesis and modeling accurately. But to do that, there is required that you have a good way of representing chemical flow sheets that enables hybrid AI. So that means a representation that is concise, complete, and accurate is required, because if you do not have a good representation, AI cannot do its magic. AI cannot find patterns in your dataset. It needs to capture relevant context, and it needs to efficiently organize information, because when we're talking about process flow sheet, you have a lot more information, and that needs to be really organized efficiently if you were to gain something out of it. So to address the representation problem, we have built something called the ES files framework, which is a multi-level hierarchical flow sheet representation framework, and it has 4 levels: levels 0, 1, 2, and 3. So I'm going to talk about these levels in the next slide. So at level 0, we have a purely text-based representation of a flow sheet, just like the smile strings. For example, if you have this flow sheet, which is, by the way, for the HDA process, hydrodealkylation process, you have a reactor, a flash, and 3 distillation columns. A, D, and C enter the reactor. There's a reaction that happens. It gives rise to ADCBE, and then you have these 3 separators, and then purge, 2 recycle streams. And there are 2 reactions which happen within the reactor. This is the main reaction, and this is the side reaction. So if you were to represent this flow sheet purely using a text-based representation, you would use something called S-files, which was proposed in this paper by Professor Ghani and his student in 2017. So S-file stands for Simplified Flow Sheet Input Line Entry Scheme, which is basically the analog of SMILES for molecules. So all the unit operations are now process atoms. So you can look at these things as process atoms, and the streams become the bonds. So they are connecting the processes together, right? So that is a bond, and that's where now you can use the SMILES analogy to represent them using something like SMILES. And recycles are captured using special symbols and so on. So the text-based representation of this flow sheet is this. Now this might look pretty complex, but let me explain what different components are. So the reactor is represented as this. So you have the indicator R, which indicates it's a reactor, and then you have the input stream, ADC, and B is coming from here, and then ADCBE, which is the product stream. Then you have flash, which is represented with F symbol, followed by the top stream, AD, and the bottom stream, ADCBE. Similarly, for distillation columns, you would have D, followed by top stream, AD, and CBE, and so on. And the recycled streams are indicated by numeric numbers. 1 means that the first recycled stream exits the process at this point and re-enters at this point. And the 2 here represents the process, the recycled stream leaves from this point and re-enters at this point, and so on. So basically, there is a set of rules, there is a set of underlying structure that can be used to convert any flow sheet to a simple text-based representation. Now that we now that we had a text-based representation of flow sheet, it has to be formalized. If one were to apply this for thousands of flow sheets or scale it up. So this is where my work came in. We developed something called S-files grammar, just like this SMILES grammar that we saw earlier. And this is how the S-files grammar looks like. So again, if you may recall, any grammar is basically a set of recursive rules, and it contains 4 main things. The first thing is a start symbol. This was SMILES for molecules, but we have defined this as S-files for flow sheets. Then you have a set of non-terminal symbols which capture meta information, or domain information about a given flow sheet. So in the case of molecules, it was chain, branch atom, bond, and so on. In the case of flow sheets, you have the separator type, the distillation column, the equipment, whether it's a process atom, whether it's a process group, whether it's an outlet, or maybe whether it's a stream, product, reactant, and so on. So these are all non-terminal symbols. Then you have terminal symbols, which are basically the symbols that you're using to actually write the S-files string. And these are R, D, A, B, C, D, and so on. And finally, the collection of these rules is basically the syntax rules or the production rules. So now if you take a very simple process like this, which is a reactive flash. So A enters, there's a reaction which happens to give rise to B and C, and then B and C are separated using this. So the S files representation for this would be this IA, indicating that A is the input, then reaction with A giving rise to BC as product, and then OB and OC are the outlet B and outlet C. Now, if you use this grammar that we have developed here, you would again get a hierarchical tree structure like this. So the leaf nodes again correspond to these symbols, and all the intermediate symbols and the intermediate rules indicate how were these symbols arrived at by sequential application of these grammar rules. Now, the application of this is that now that you have a grammar, you can automatically parse any S files string using a program, and you can check for the syntax, right? If you have 500 flow sheets, you can find out which of them are incorrect flow sheets based on the grammar that you have defined using these grammar rules. Then you can also assign structure, just like we assign structure to a smile string using the smiles grammar. We can assign structure to any S-file string using the S-files grammar. And now that you have a structure, you can infer connectivity information automatically. You can know that, how is this A connected to maybe this B here, or how are different unit operations connected with each other. So that sort of inference is possible. And we use exactly this grammar with the level 0 S-file strings to construct the level 1 flowsheet representation, which is a flowsheet hypergraph. So we represent at level 1 a flowsheet as a hypergraph where the streams are represented as vertices or nodes, and the unit operations are represented as hyper edges. Recall that an edge is basically a simple edge between A to C and B to C, whereas a hyperedge can connect any number of nodes together. So A, B, and C are all connected together using one single hyperedge because it's an arbitrary concept where you can connect any number of nodes that you want using one single hyperedge. So this is how the hypergraph for the flowsheet looks like. This hypergraph explicitly shows the connectivity information between the different unit operations and the different streams. So AD and C input the reactor. So this is R1, which is the hyperedge. Then ADCBE exits the reactor and enters the flash F1, which is the hyperedge. And then AD goes here, ADCBE goes here, then it goes to a purge. The pink ones are the recycle ones, and the yellow ones are the output ones, and the white ones are basically the intermediate streams. So in this way, you have explicitly represented a flow sheet using a hypergraph. Now, somebody might ask, why do you want to represent the flow sheet as a hypergraph when you already have a process flow diagram? The reason is that since the whole idea is to use hybrid AI, you would want to have a numeric representation of a flow sheet, and a hypergraph or a graph is a numeric representation. It can be understood by machine learning algorithms, it can be understood by graph-based algorithms, and this allows you to directly apply graph-based methods without having to first create a graph by looking at the PFD and then applying those methods. So going to level 2, now that we have at level 0 a purely text-based representation, at level 1 we have a graph-based representation which explicitly captures the connectivity. At level 2, we want to add some more information. That more information is flowsheet context. When I say context, I mean what's the material and energy balance information, what's the reaction stoichiometry, conversion factors for dividers, what's the divider fraction, for purge, what's the split fraction, and so on. So that contextual information is captured using something called node edge labels. What I mean by that is each node and each edge pair would have an annotation indicating the context. For example, for the node C and for the edge R1, you would have an annotation MC indicating the component flow rate for this stream. Similarly, for AD, you would have the component flow rate captured here. For the reactor, you would have the stoichiometry conversion, the stoichiometry coefficients, the conversion factors x1, and at each hyperedge, you also have something indicating E bar, which basically is either the temperature or pressure of a stream, so that you could keep track of energy balance. And if the E values change across any unit operation, that means that there is a heat exchanger or there is a pump if the pressure and temperature have changed. So in this way, you have not only not only captured the connectivity information, but you have also captured the flow sheet context, which is required for performing simple mass balance, simple energy balance, and so on. Now, at the highest level, you would want to have a representation which can be used for performing rigorous process flow sheet simulation. And for this, you need to store a lot more information than just material flow rate or conversion factors and so on. So because you have so much information, we need to organize that in an efficient manner, and that is why we developed a process ontology, which has a main class called process atom, and then operation and design classes, which capture the operation and design information of the different unit operations. And for the operation, we have different information for the incoming and outgoing streams. And an instantiated ontology is connected to each of these process atoms so that you have all the information here. For instance, for the reactor, you would have R1 as the name of the process atom, and then the incoming streams, the outgoing streams, and the temperature, pressure, phase, composition, rate, flow rate, and so on for the incoming streams, same for the outgoing streams, and then the reactor specific design information. So this is at the highest level, and the idea is that this could be used for flow sheet simulation. Here's the entire framework snapshot. Like I mentioned, level 0 is the simplest one with purely text-based representation. At level 1, you have flowsheet connectivity information. And now, since you have that, you can connect that with any flowsheet generator to get multiple different options for the same flowsheet based on certain constraints. At level 2, you have mass and energy balance information as well. So now you can give it to a simple process simulator, perform basic calculations, and with that, you level 3, which can be connected to a process simulator, which is much more advanced, so that you can perform much more detailed simulation results could be obtained from the process simulator. This is again, still work in progress. As we go forward, we would want to add levels 4 and 5 so that we can add process safety, process control, and all of those information as well. So I have one more section of my talk. So not sure how much time I have, Professor.
You may continue it because we have around, well, we have at least 10 minutes and then the questions.
Okay.
You can go on. Yes.
Okay, cool. So yeah, I think 10 minutes is it's going to be enough. So okay, so in this last section of my talk, I'll talk about one level higher. So if you have pharmaceutical documents, how can we extract information from them? Again, using the same concept of domain knowledge combined with language models. And this work was done in collaboration with a pharmaceutical company called Eli Lilly. And the idea was as follows. So these companies, pharma companies, they have been in existence for hundreds of years or at least several decades. So they have a lot of unstructured data in the form of text documents. And unstructured data is any data that does not have a predefined schema or predefined column names and everything. So, like I mentioned, this is terabytes of data containing electronic lab notebooks, process description documents, regulatory documents, and so on. And a lot of this gets is unutilized because they are in unstructured format. So you would not know how can you leverage them because you cannot train machine learning models. You cannot look at them visually because they are all unstructured. So the objective was, can you take all of these documents, convert them into structured documents, and extract actionable insights from them? What I mean by that is, if you can consider this example sentence, it's talking about something about cell growth assessed by some method, which is using some salt and some cellular process and resulting in some product formation. For a machine to understand this, the first step would be to automatically identify the important words in this sentence. So the important words are cell growth, staining method, tetrazzolium salt, formation product, and dehydrogenases. The next step is that you don't just want to identify the important words, but you also want to identify the context. So the context is that we're talking about cellular dehydrogenases and we're talking about a colored formation product. And finally, the third step is to identify the relations. How are these different words, concepts connected with each other so that in the end you could create a knowledge graph like this. Now, in this knowledge graph, you can see that this is a structured representation of this sentence. It says that the cell growth is assessed by a staining method, which is using this salt, and this salt is converted to this product, and this is converted by this process. So our objective is to go from terabytes or megabytes or gigabytes of data, which is in this format, to this format so that we could derive some actionable insights. So to do that, we have developed a framework that goes from, like I mentioned, text documents to knowledge graphs. And we have called this framework, we have named this framework as SUSY, which stands for Schema-Based Unsupervised Semantic Information Extraction. Because we are using an ontology, so that's why the schema is completely unsupervised, so you don't have to label anything. It preserves semantic information, and so that's why the name SUSY. So let's look at the details of this. So SUSY has three main modules. The first module is a weak supervision framework, which can be used to programmatically annotate important words. Because all we were given was unlabeled data set, just bunch of text documents. We did not know which words are important, which words are not important. So we first had to programmatically annotate those important words. Second is training a machine learning model, and third is relation extraction to create that knowledge graph. So looking at the first module, and this was the most important module, how can you automatically annotate a set of documents where each word is labeled 0 or 1, where 1 indicates important word and 0 indicates unimportant word. And for this, we use domain ontologies combined with NLP matching algorithms. So ontologies are basically a formalization of domain knowledge where you organize domain knowledge in the form of class, subclass, and properties as a hierarchical structure. There are standard ontologies within the unified medical language system. So it has 1 million biomedical concepts, 5 million concepts, and so on. So basically, think of ontologies as a dictionary which is organized in a hierarchical manner so that you have the semantics. So a lot of our work was done because of efforts by the unified medical language system. So we got access to this. But then since we were working with a pharma company, they wanted us to customize it for them. So we also developed our own ontology, which captures the information that you need for drug manufacturing. So here is a snapshot of the ontology that we built. So in reality, this contains thousands of classes, but this is only a preview of what we built. So the main class is drug manufacturing. And drug manufacturing, when you talk about drug manufacturing, you would talk about design specifications, the material properties, the risk factors, and the different kind of materials that are used. And if you look at design specifications, you would look at the design requirements. What's the requirement in terms of design for a given process, the design attributes, the equipment used. For material properties, you have compositions, flow properties, physical properties, solid phase properties, and so on. So basically, this ontology was developed to hierarchically capture all the important concepts and synonyms that you might need to label as important. And once you define this, now you can combine this with NLP matching algorithms to automatically label whether a given word is important or not. So now we have gone from unstructured text documents to unstructured documents, but with labels indicating whether those words are important or not. Now that we have a labeled data set, we can use the power of machine learning based classifiers. And the whole idea is that the classifier would predict whether something is important or not. So it's a binary classification. And again, the choice of machine learning based word classifier was based on a language model called BioBERT, which was a pre-trained biomedical language representation model. So the good news is that this is a pretty extensive model, which was trained on 4.5 billion words, 13.5 billion words from this full text articles from PubMed, and then, of course, a lot of English words as well. So good news was that we did not have to train such big model from scratch, but what we did was we fine-tuned it. We adapted it for our dataset by fine-tuning it on our dataset so that it understands some specific words from our uh, company-specific documents that we received. So this was the classifier. And finally, the third aspect is once you have the machine learning-based classifier, you would want to extract the relations between sentences. And the idea that we use for extracting relations is as follows. Whenever you have a sentence, you can always extract semantic triples of the form subject, predicate, and object. For example, if I have this, tetrazzolium salt is converted by cellular dehydrogenases. So I know that this is the subject, this is the predicate, and this is the object. And I can link them together, and I have a knowledge graph. And for extracting such triples, we use this open source tool called Stanford OpenIE, which extracts these triples automatically from a given text. And there's a lot of details to it. It's a very simple approach, but it's not simple to implement because you have to find out the same person, the same entity might be referred in different ways. For example, I, my, and she are all referring to the same thing here. Nader and he are the same thing. So all of those complexities are taken care of by Stanford OpenIE. And in the end, we extract the entities, we extract these triples, and we combine them together to create a knowledge graph. And this is the overall approach. And in the end, all you need is a machine learning based classifier to create such knowledge graphs. So let me skip over these. These are the model training aspects and some performance. And let me show you an example of how the knowledge graph looks like. So if I have take this paragraph, which is from a published document about a certain drug called evacetrapib, and this contains a bunch of technical documents, technical words and technical information. The first step is identifying the important words, important information. So Suzy identifies automatically all of these words as important. The next step is to convert these words into a knowledge graph by extracting the relations. And the first knowledge graph that we get is this. So it says evacetrapib is a novel CETP inhibitor, which is with favorable effects on plasma lipids. Then it says evacetrapib is a CETP inhibitor, which is of potential benefit. The second knowledge graph that we have is it says there is a hope that you would elucidate off-target toxicities of torcetrapib, which is some other chemical. And the third thing is the third knowledge graph it captured is enthusiasm decreased as a result of adverse clinical outcomes. So you see that Suzy using this approach, Suzy was able to capture the essence of the text in the form of these knowledge graphs. So it gives you a visual connected representation of important information across various documents. And the question is that, if we give these things to ChatGPT, will it be able to write a good summary? So we provided these knowledge graphs to ChatGPT as input, and it wrote a pretty good summary of what is being talked about in this knowledge graph. So it could also be used as a good summarization tool for people to, just glance over important information in a unstructured text. So a lot of information about Suzy, and this is what we filed a US patent application for, because there's a lot of things. It's not just a prototype software. We have done extensive programming and extensive software building, which does end-to-end document pre-processing, entity recognition, contextualization, relation extraction. We also did semantic search. So, but all of that information you should be able to find in this paper that we published on this. So in summary, let me wrap up my talk with this. So you might have, I hope that I have shown how combining domain knowledge into language modeling frameworks offers a lot of benefits. At the model level, we saw how reaction prediction problem is simplified, leads to more accurate predictions, leads to few grammatically incorrect predictions when you combine them with domain knowledge in the form of Smiles grammar. For the chemical flow sheet level, we saw how if you come up with a new representation which captures flow sheet information at different levels, your flow sheet synthesis and design problems are much more simplified and enables the use of hybrid AI applications. And for this, we saw how we can use ontologies to perform weak supervision so that your unstructured documents could be converted to labeled unstructured documents, which could then be converted to relation extraction. And again, since we looked at different levels of this applications of language models, our hope is that this would guide the community in the right direction in the sense that we should build first principles based or more domain informed AI models or language models and not purely data driven approaches. And the talk might have given you a gist of the different ways in which that could be done, different representations, adapting the problem formulation, coming up with custom model architectures, ontologies, and domain constraints, and many more. So these are the list of publications that came out of this work, and feel free to take a deeper look at this. I'm happy to chat more. And finally, I want to thank you for the attention. I know it's been a lot of information dump on you, but I hope you probably would have gotten something out of it. And I also want to thank Professor Maurício for inviting me here and the collaborators and the funding sources. So thank you very much. Looking forward to your questions.
Thank you, Vipul. Thank you very much. I think that all the community, the PSE community is interested in working with large language models, and we are still approaching the subject, the community in general, but you have worked a lot in your PhD and have proposed different ways to work. All of them are very interesting. You see the reaction prediction and the prediction of properties and the representation, the flow sheet representation, and all
Right.
integrating the domain knowledge that we know in general that if you are using artificial intelligence, if you add this knowledge, it is probably going to work better. So your presentation was very good and inspiring. And
Thanks so much. I'm glad I could do justice to people's time. I remember professors skipping the classes for this talk, so really thankful that that worked out. And no, you're right. That is a very interesting area, and it seems like I may have worked a lot in my PhD, but I think it's all very interesting problems. And once you start working on something, then it becomes even more interesting to solve them and see the results. So
yes, and I think that you are kind of working with people that, for example, Professor Venkat worked with artificial intelligence for long years, and also you worked with Professor Gani too. That
right, yes, that's right.
it's very important in terms of PSC. So I am going to open for questions, and I think Professor Ajimiru has opened his camera. So I think, yes, he has also raised his hand. I will pass the word to Ajimiru.
Okay, thank you, Maurício. I think you already mentioned a lot of things regarding to this presentation of Vipul, which was very impressive presentation, Vipul. Very nice work that you have done in your PhD. Yeah,
Thank you.
this molecular level adaptation of Smile language to this Smile grammar that you developed. Then you extend that from sheeting and also the documentation. Very nice work. And you put everyone these methodologies in the same ground, now the graph theory and so on, and the large language modeling. My question is regarding to the second part of your talk, regarding to the S files
Mhm.
that you have presented. You mentioned that together with the S files grammar, you also develop ontology to model the level, I think level
Right.
3 flow sheet. Yeah.
Yeah.
And what this ontology that you have developed has a relation with that already developed the OntoCape.
Right.
Uh,
Yeah.
they are the same standard. They can talk with each other. These ontologies.
Yeah, so that's a great question, and that's something we get all the time. So you're right, OntoCape, and I would say that OntoCape is actually much more comprehensive than what we have developed because it has classes for mathematical equations, it has classes for different processes, unit operations, and so on. So in this work, our objective was to show a conceptual model of what we could do with this multi-level representation. So the idea was that to get the point across that if you want to store information about process simulation, you need to have an ontology that is specific to your use case. And initially, we wanted to keep it simple because the way we have represented the flow sheet is in the terms of process bonds and process atoms. So your process atoms are unit operations and process bonds are streams. So that we do not lead the user towards being confused as to what's a process atom in the OntoCape ontology, what's a process bond in the OntoCape ontology. We started off with a very simple ontology, a process atom with streams and then unit operations and all the details. But yeah, I think you're right. As we go forward, we actually plan to incorporate some of the classes from OntoCape or maybe borrow some of the classes from OntoCape without having to reinvent the wheel and so on.
Yeah, that will be very nice because there is a initiative as many software providers and institutions, the research institutions that are trying to develop a standard in the ontology for process system engineering,
Right.
and more than AutoCAPE, more general than that, more standards. And then if all these ontologies can communicate with each other, now that you can do a lot of good
Yeah,
things.
yeah, yeah, you're right. I think it's also gonna facilitate the communication, right? Like if someone says that maybe this class has to be a different way, then everybody would know which class they're talking about and what's the context. So that's
Yeah.
a good point. And Yeah, and I guess, as we go forward, like I mentioned, your process control, when things like process control come in, things like process safety come in,
Exactly.
I don't think we should be developing ontologies from scratch because world experts would have already developed those ontologies for us. So
Yeah, then you can organize all the data that comes from the ground of the industry, and then
right,
model the data and do everything else in real time and do a lot of
right,
things together.
yeah,
Yeah,
yeah, that's a good
great.
point.
Like, nice job, great. And that's my
Thank you.
question.
Yes, we have time for more questions. Andrea Parenti, which is our colleague, a professor at the School of Chemistry, has raised her hand. So I will pass the word to Andrea.
All right, thank you, Professor, and thank you so much for your presentation. I'm an AI enthusiast, and I'm
Okay.
very interested in studying your work because I think there are a lot of things that we can keep on researching. And I was wondering if you have tried to combine your solutions. So maybe, for example, have you tried to use grammar to VAC along with the reactions predictions and inverse reactions predictions?
So yeah, that's again, great question, and I think I can see that you're very deep into machine learning because that's a very deep question. So if you look at the transformer architecture, right? Let me see if I can go back to the slide. The transformer architecture automatically learns a vector-based representation when you give a reaction as input. So let me quickly go to that. Yeah, here. So if you look at this, right, so here you have the input embedding. So that means that the inputs for the forward reaction would be a set of reactants. And the first step is to convert each of them to an embedding. So this embedding is happening at the very first stage. And then you are adding something called positional embedding, positional encoding, because when you're talking about reactions, the position of the tokens, the position of the words is important. Whereas in the case of grammar 2 you just have one molecule, so there is no notion of position. So the input embedding plus the positional encoding gives you an embedding for the reaction, and then the whole, the transformations and predictions and all of that thing happen within these blocks. And the interesting thing about this is that even these embedding parameters are learned as you train the model. So that's a good point, but the embedding portion is being taken care of within the transformer architecture. But related to this, something interesting that I can think of right now, I'm not sure if I'll have the time to work on it given my current day job, but something interesting that I can think of is that if you have, let's say, 500,000 reactions, and if you extract this layer and compute the embeddings, do you find out reactions that are similar based on a chemist understanding are also similar based on the embeddings? So if someone does that sort of study, do we see the same clusters? Do we see the same classes of reaction, the same category of reactions as a chemist would say? If that is the case, then we can say that such models really capture a chemist's understanding and can be more trustworthy. And if not, then I would question whether this thing even works or not. I hope that answers your question, Andrea.
Yes, yes. Thank you very much for clarification. I wish we had more time to keep discussing, but yeah, thanks for sharing.
Yeah, thank you for the question. And so just a note to everyone. So even though I'm working, full time as a senior manager biomarker data scientist at BMS, I'm still actively working with Prof Venkat. So I'm open to any questions, any interesting discussion that anybody might want to do, even after this session.
Thank you, Vipul. Does anyone want to comment or make another question? Gustavo, please.
So, Vipul, thank you for your presentation. My question, I have actually two questions. One is that in process simulation, I think because large language models, as you said, they use like a sequential modeling, you could use also to solve like large simulations because since there are sequential modeler uh,
Right.
solvers. So I think that's a kind of good approach. And my second thought was regarding process control. Do you see any application of large language model in process control?
Okay, so again, yeah, amazing question. So to answer your first question, on the face value, if you look at it at a high level, things might seem to be suited for language models. You might think that, since in a process simulation setting, you have a sequence of unit operations, so language models might apply. But the challenge over there is that, language models are inherently limited in the sense that you have to only give text-based representation. And if you want to do flow sheet simulation, you have to give a lot more information. Like I mentioned, all the information that you have in an ontology, or all the information that you have as various annotations, like the process flow sheet, the process flow rate, the reaction conversion factors, and lot more parameters. So giving those as input in a language model, I think that is going to be pretty challenging. But what I see for sure is that a combination of language models, a combination of machine learning models, and a combination of domain knowledge based heuristics, which should be combined to build a framework that can solve those problems, and not just solve those problems efficiently but also accurately. Because as for a reaction or for a molecule, things are fine because the context can be given indirectly with a representation that is better. But if you go to process flow sheet simulation, there is this whole world of context that needs to be captured, and at this stage I feel the language models are not really able to capture them entirely. So certain pieces of that problem could be solved using AI, using machine learning, but a large portion would still depend on traditional simulation or traditional domain knowledge. And your second question was about, what was your second question about? Right. Yeah. So when you talk about process control, so I think at this point we are not really we haven't thought about that in detail. But going forward, maybe in terms of improving the efficiency, we can see the use of AI or hybrid AI to in process control, but it is still largely a very controlled and a very first principles based area. So we are thinking of extending the ES files to support process control, but we are not thinking of using purely data-driven AI or a largely data-driven AI to do process control at this point. But we are actively exploring process control ideas, safety ideas, and also flow sheet alternative ideas. So because I think in process flow sheet domain, process simulation domain, there is a lot of problems to be solved. So we are at a very initial stage in that matter. Yeah, sure. Thanks for the questions.
Okay. Vipul, just to keep the schedule, because I know that other people would be interested. I know that we are going to dive into your works, you see, and then maybe we can talk to you in another opportunity. But thank you very much. It was really, as I said, inspiring and a way for us to go working more closely with these large language models. So thank you very much. I would like also to announce our next seminar that will be on April the 8th, uh, 2 weeks from now, and it will be presented by Afrânio Melo. Afrânio is from, he is a doctor, he is from Petrobras, and his presentation is entitled Open Innovation in Process System Engineering, Bridging Academia and Industry through Open Source Projects. So you are all invited. And Vipul, thank you very much again for your presentation and for your generosity being here and presenting your research. Thank you very much.
Thanks for the invite, Professor. It was really a great experience, and it was nice to hear all the questions, feedback. So, and like I mentioned, please feel free to reach out to me over email, and I'll try to respond to your queries in 1 or 2 days, not more than that. So, thanks again for the
Sure.
invitation, and thank you for having me. And have
Thank
a good
you.
rest of your day. Thanks.
Thank
Bye.
you, everyone. See you then.